Sometimes you hear about AI doing things that just make you pause and go, wait, really? Like solving really hard math problems.
Yeah, the kind you see in things like the Math Olympiad, AME, HMMT level stuff.
Exactly. Problems that stretch even brilliant human minds. And, well, that's what we're diving into today.
We are. There's been some, frankly, astonishing progress in AI mathematical reasoning lately, and we're looking at a specific, very recent breakthrough.
That's right. We've got this paper, AAO to Winning Solution, Building State-of-the-Art Mathematical Reasoning Models with OpenMathReasoning Dataset. So think of this as our mission, yours and ours, getting the inside scoop on how AI cracked these super tough math challenges.
Challenges thought to be, firmly human territory until recently.
We want to figure out the key ideas, the innovations, and why this is such a big deal, not just for AI, but maybe even for how we think about solving hard problems. It's like a shortcut to understanding some pretty dense research.
And our source is this technical paper detailing the winning submission to the AI Mathematical Olympiad Progress Prize 2, AIMO2 for short.
And the headline result is, well, pretty mind-blowing. This AI system solved 34 out of 50 extremely difficult unpublished math problems.
And under really strict conditions, tight computational limits.
It won first place.
Which tells you right away, okay, this is something special. So let's back up a bit. Why has math reasoning been such a tough nut for AI to crack historically?
It's a great question. Because AI, historically, it's been amazing at pattern matching, right? Tasks with very clear rules.
Like chess or Go, maybe?
Sort of, but math reasoning, it's different. It demands flexibility, abstraction. You need to understand concepts, string together multiple logical steps, sometimes even backtrack and try a whole different approach. Early models just weren't built for that kind of abstract thinking.
Right. I remember the excitement around chain of thought where the AI would sort of show its work, but it sounds like this is going even further. Well, yeah, much further. The paper talks about moving towards long reasoning models. It's not just about listing steps anymore. These models engage in a more, let's say, extended thinking time.
Thinking time.
Yeah, they can reflect on their own reasoning, explore different paths, tweak their strategy. It's that ability to self-critique and adapt mid-problem that's been, well, a real game changer for complex math.
Okay, so this AIMO2 competition, it sounds like it was designed specifically to push these new capabilities.
Yeah.
What made it such a rigorous test?
A couple of things made AIMO2 really stand out. First, the problems were hard, like National Math Olympiad hard.
Wow.
But maybe even more critical, they were unpublished, not floating around online anywhere.
So the AI couldn't just, find the answer in its training data.
Exactly. No memorization shortcuts allowed. It had to actually reason. Second, the constraints were serious. A 5-hour time limit, and only 4 L4 GPUs.
4 GPUs, that's not a supercomputer cluster.
Not at all. So forget brute force. It really boiled down to the quality of the AI's mathematical thinking.
Unpublished problems, tight resources. That definitely ups the ante. Okay, so let's get into the winning solution. What were the key breakthroughs that let it succeed there?
The paper really highlights 3 main pillars working together. First, building a massive new data set specifically for this kind of long reasoning called OpenMathReasoning.
Okay, data, always crucial.
Second, a technique they call tool-integrated reasoning, or TIR.
Tools, like calculators.
More than that, as we'll see. And third, a method for picking the best answer when the model generates several possibilities, called Generative Solution Selection, or GenSelect.
Okay, dataset, tools, selection, let's break those down. Start with the OpenMathReasoning dataset. What went into building that? Sounds massive.
It was a huge undertaking. They realized that to train AI for deep reasoning, you need tons of examples. So they collected problems from the Art of Problem Solving forums, AOPS.
AOPS, a goldmine for math problems.
Definitely. They grabbed basically everything except the middle school math section, figuring that was a bit too basic for their goals. This first pass yielded about 540,000 unique problems.
500,000.
Yeah.
Oh, how do you turn messy forum posts into something an AI can learn from?
That was the next challenge. They built a pipeline using another large language model, Qwen 2.532b Instruct, to systematically extract the actual problems, and, for non-proof questions, the answers from those forum threads.
So pulling the signal from the noise, basically?
Pretty much. Identifying the core question and answer within potentially long discussions.
But wait, if it's all from the web, how did they ensure the AI wasn't just seeing problems it already, knew from its general training?
Excellent point. That's where benchmark decontamination comes in. It's critical. They used an LLM to compare their collected problems against existing math benchmarks.
Like a plagiarism check for AI training?
Kind of, yeah. If a problem looked too similar to one in a known benchmark, they toss it out. This ensures the model is evaluated on truly novel problems, forcing it to reason rather than just recognize. The paper actually references earlier work stressing how vital this is.
Smart. Okay, so after all that collecting and cleaning, what did open math reasoning actually look like? Size, content.
The final dataset ended up with 3.2 million long reasoning chain of thought solutions. These were generated by prompting strong models like DeepSeek R1 and QWQ32B on those 540K problems.
3.2 million solution.
And importantly, it included converted math proofs too, some with answers extracted, some without. When you stack it up against other AOPS-derived datasets like AOPS Instruct or NuminiMath 1.5, OpenMathReasoning is significantly larger. Scale was definitely a goal here.
Got it. A massive, carefully cleaned library of problems and detailed solutions. Now, pillar number 2, tool integrated reasoning, TIR. What's the core idea?
TIR is about mixing that natural language, step-by-step reasoning the chain of thought style with the ability to call external tools, specifically here, executing Python code.
Ah, so the AI can think in words, but also say, okay, let's run some code for this calculation.
Exactly. It combines the sort of human-like reasoning flow with the precision and power of computation.
That sounds powerful. How did they teach the AI to do that? Where did the training data come from?
Well, they started by prompting a model called LimoQuin32B to generate solutions that used code. But they ran into a quality issue.
The code wasn't always helpful.
Right. Sometimes it was trivial, like just checking arithmetic you could do in your head,
Oh.
or sometimes completely irrelevant. So they realized they needed a strong filtering step.
Filtering for usefulness.
Precisely. They wanted to keep only the examples where the code provided a real, substantial reasoning advantage. Things like using numerical solvers or running an exhaustive search that would be tedious or impossible for a human.
How did they judge substantial advantage? That sounds subjective.
They developed criteria. They classified each code block based on its novelty. Did it produce a result not already figured out by the text reasoning? And its significance, did it solve a trivial, moderate, or significant part of the problem?
Okay.
They actually used another LLM, Quen 2.532B Instruct, to help make these judgments, alongside some rule-based filters, like tossing out solutions with wrong final answers or ones that weirdly didn't even run any code. And initially, they found limiting solutions to just 1 or 2 code blocks helped focus the quality.
So really curating examples where code was a strategic asset, not just decoration. What came after that first filter?
They took that high-quality, filtered TIR data and used it to fine-tune a better model, QWQ32B. Then they used that fine-tuned model to generate more TIR solutions for the whole OpenMathReasoning dataset.
Ah, an iterative process. Generate, filter, fine-tune, generate more.
It's exactly. This new batch, about 700K samples, was filtered again, mostly focusing on correctness and making sure code was actually used. The novelty significance filters weren't as needed this time. They did one more round like this with a 14B parameter model. This whole iterative refinement process resulted in their final TIR dataset, 1.7 million high-quality examples.
1.7 million examples of code-assisted reasoning. That's impressive. The paper mentions something about controlling how often the model used code.
Yeah, that was a neat little trick. When generating the data, they included a message in the code output like, you have Xcode executions remaining.
Huh. Like giving it a budget.
Kind of. And they noticed the model often paid attention to this in its own internal thought process and would stop trying to use code once the budget ran out. During training, they simply discarded examples where the model tried to exceed its allowance, reinforcing the behavior.
Clever. Okay, so now the model can reason step-by-step and strategically use Python code. That feels like a big upgrade. What about the third pillar, GenSelect? Generative Solution Selection.
All right, GenSelect. The motivation here was bridging a gap. They noticed their models were often capable of generating a correct solution if given multiple tries, say generate 64 solutions and pick the majority answer, majority at K. But getting it right on the first try, pass at 1, was harder.
Okay, so it knows the answer is in there somewhere, but picking it out is the problem.
Exactly. GenSelect is about training the model to be better at picking the most promising solution from a set of candidates it generates itself. The key insight was that comparing multiple solutions side by side seems to be easier for the model than judging a single solution in isolation.
That makes intuitive sense, like looking at a few different rough drafts to see which one feels right. How did they train it to compare?
They generated sets of candidate solution summaries for problems anywhere from 2 to 16 summaries per set. Critically, each set had at least one correct summary and at least one incorrect one.
Mix of good and bad options.
Right. They repeated this to get 8 different comparison groups per problem.
Hmm.
Then they used the QWQ32B model to choose the best summary from each group. After filtering out cases where it picked incorrectly, they had about 565,000 high-quality selection examples to train on.
So it learned this summary looks more correct than that one, but comparing even summaries sounds computationally intensive if you do it a lot.
It could be. So they optimized. They trained models to directly generate a comparison summary, rather than needing the full reasoning for each candidate during selection. They found Qwen 2.5 32B Instruct was good at creating these effective comparison summaries.
So the model generates a summary about the comparison itself.
Yes,
Okay.
essentially. And models trained this way performed almost as well as those comparing the full reasoning, but way faster. Made GenSelect practical.
Okay, so those 3 pillars. The massive OpenMathReasoning dataset, tool-integrated reasoning, and this GenSelect comparison method. They all came together to create these OpenMath-Nemotron models.
That's the result. A series of open-weight models, 1.5 billion, 7B, 14B, and 32B parameters, built on the Qwen 2.5 base architecture.
Open weight meaning others can use and build on them.
Exactly. An interesting detail for the smaller 1.5B and 7B ones. They started with math-focused versions that initially had limited context window. They couldn't handle super long chains of reasoning.
Ah, so they needed to fix that.
Yeah, they used a technical adjustment, changing the row P base for those interested to extend that context window significantly.
And the training involved all 3 elements. COT, TIR, GenSelect?
Yes. The models were trained for 6 epochs, 6 full passes through the data on a mix of COT, TIR, and GenSelect tasks, each triggered by a specific prompt format. The total combined SFT dataset had 5.5 million samples. They used standard stuff like the Adam W optimizer, cosine learning rate decay, standard deep learning training techniques.
And how did they perform?
Very well. On benchmarks like CompMath 2425 and HLE Math, they showed really strong performance, especially the bigger models, outperforming other strong open models like DeepSeek R1 Distill Qwen.
Okay, so a family of powerful math models, and it was a specific version, likely the 14B one, that won AIMO 2.
Correct. But the winning Kaggle submission had a slightly tailored training recipe compared to the general OpenMath-Nemotron release.
Oh. What was different for the competition version?
For the competition entry, they fine-tuned the Qwen 2.5 14B base model for 8 epochs, but only on a subset 2.2 million samples of the chain of thought solutions generated just by DeepSeek R1, and they excluded the converted proof problems.
More focused training data.
Seems like it. Then they did a very lightweight fine-tuning pass on just 15,000 of the initial high-quality TIR samples, and then they used model merging.
Merging, like averaging 2 models together.
Pretty much, yeah. A simple linear combination averaging the parameters of the model checkpoint saved after the COA-T training and the best checkpoint from the TIR fine-tuning. Interestingly, they didn't use GenSelect training or inference for the final Kaggle submission.
Huh. Why merge them? What's the benefit?
It seems it was a way to get the best of both worlds. The strong core reasoning from the extensive COA-T training, plus the tool-using ability from the TIR fine-tuning, without maybe some of the complexities or potential downsides of deeper TIR training. The paper notes it also seemed to speed up generations, slightly shorter solutions, fewer code calls.
And speed was everything in that competition, right? What else did they do to optimize for that 5-hour limit?
Oh, they went all out on inference optimization. They used NVIDIA's TensorArt LLM to compile the model into a super efficient format.
Like tuning an engine for max performance.
Exactly. This gave them things like in-flight batching processing multiple problems concurrently, very efficiently, custom attention kernels, page KV caching for memory management, and quantization.
Quantization, making the numbers smaller.
Essentially, yeah. Using lower precision numbers like INAD8 or FP8 for the model weights speeds things up a lot, often with minimal accuracy loss if done carefully. They also use speculative decoding with something called redrafter.
Speculative decoding.
It uses a smaller, faster drafter model in this case, an RNN trained on their OpenMathReasoning data to predict a chunk of text. The main model then just verifies it, which is much faster than generating word by word. They reported getting several draft tokens accepted on average.
Okay, faster generation. How did they manage the whole process during the comp?
They used a system called NEMO Skills with a FastAPI backend. This handled batching the problems, enforcing time limits per problem, stopping things that were running too long, and managing the code execution.
This code execution needed careful handling, I bet.
Absolutely. NEMO Skills provided a sandbox Python environment with strict limits, Max number of code calls, timeouts, limited output size, crucial safety features when running arbitrary code generated by an AI.
That is a ton of engineering layered on top of the core AI model. Just incredible attention to detail.
They really needed it to meet those tight constraints. And it paid off.
Yeah, 34 out of 50 problems solved on the private leaderboard. First place, an amazing result.
It truly validated the whole approach.
Mm-hmm.
The data set, the reasoning techniques, the optimization.
It's also interesting how they reflected afterward. They mention a later model, which looked better in testing, didn't actually do as well in a rerun simulation. Why might that be?
They had a few ideas. One, the public leaderboard was small, so scores could jump around a lot, high variance. Hard to know if an improvement was real.
Right, noise in the measurement.
Also, they noticed smaller models sometimes did surprisingly well locally, but didn't generalize perfectly to the competition, maybe due to specific hard problems or just differences in the problem sets.
And didn't they mention something about solution length?
Yes, that their later, seemingly better models actually produce longer solutions on average. In the competition's dynamic time allocation, where solving easy problems fast gives you more time for hard ones, longer solutions could actually be a disadvantage, even if technically more thorough.
Huh. So being smarter isn't always faster in a time setting. Lots of subtle interactions.
Definitely. It shows that evaluating and deploying these advanced models in real-world high-stakes scenarios is still complex. There are always nuances.
The paper also rightly gives credit to related work, placing this in context.
Yeah, they acknowledge the history, mentioning things like Program of Thoughts for tool use and other big math datasets like Skywork Math QA, Numina Math, OpenR1 Math. It shows this is building on a whole community's efforts.
Absolutely.
Okay, let's try to crystallize the main takeaways from this deep dive. What are the headline points?
I'd say, 1, the creation of OpenMathReasoning, a huge, carefully decontaminated dataset, was foundational. 2, tool-integrated reasoning, effectively blending language reasoning with code execution, was a major capability boost.
Right.
3, generative solution selection shows a path to improving reliability by having the AI compare its own potential answers. And 4, putting it all together in the OpenMath-Nemotron models and then hyper-optimizing a version for the competition led to state-of-the-art demonstrable success.
And for you listening, what's the broader significance here? Why should you care about AI solving Olympiad math? Because it's a concrete, powerful example of AI moving beyond pattern matching into genuine, complex reasoning. It's tackling problems that require deep understanding, strategy, and tool use, much like humans do, in a notoriously difficult domain. It's not just calculation, it's about the process of finding the solution.
Which really opens up the question. As AI gets better and better at this kind of reasoning, where else could that lead?
Exactly. That's the final thought to leave you with. If AI can reason through complex math, what about complex problems in, say, science or engineering? Or drug discovery? Could this kind of advanced reasoning capability accelerate breakthroughs in fields far beyond mathematics? It prompts us to think about what intelligence really means and how AI might augment our own.
A really profound thought, and it's fantastic that they've released the code, the models, the data set. It fuels further progress.
It does. It makes this cutting-edge research accessible and allows the whole field to build upon it. Really exciting times for AI reasoning.